Welcome
Welcome
to lesson
to
5.1.
5.1.
Today we're going to talk about recognizing linear functions. And in linear functions, you'll notice that it says, or it has the word line. So when we're talking about linear functions, we're talking about functions that give us a graph of a line. Right? Okay. So first of all, we're going to take a look at this graph here where we have these plotted points. When the race car driver drives for an hour, they go a distance of 210 miles and so on and so forth. You'll notice that each of the plots goes up, and if we were to connect them, it would be in a line. So first what we're going to do is we are going to fill out the table as you guys did before. So we know that when x is 1, y is 210. And we know that when x is... Obviously, I have a little person here with me while I'm trying to do this, so bear with me here, you guys. When x is 1, we know that y is 210. And that when x is 2, y is 420. When x is 3, y is 630. When x is 4, y is 840. And when x is 5, y is 1050. So the first thing that we are going to do is we are going to take a look at the change in x. Alright, so when we look at the change in x, when we start, we're going to look at the change between 2 and 1. And we know that the difference is 1. Then, if we look at the change in x between 3 and 2, again, the difference is 1. And between 4 and 3 and 5 and 4, the difference is also 1. So we notice here that in this function there is a consistent change in x. Alright, so now we're going to check to see if there is a constant change in y. To start off, I take 420 minus 210 because that's the first 2 points, and I notice that there is a difference of 210. Then 630 minus 420, again, I get a difference of 210. And on the next one, I have 840 minus 630. I have a difference of 210. And then I have the last one, which is 1050 minus 840, which is a difference of 210. So I'm noticing here that I have a constant change in y. So when I look at this, I know that there is a constant change in x and a constant change in y. And the constant change in x that corresponds or goes with the change in y is that every change in x of 1 corresponds with a change of y of 210. So anytime my x changes by 1, my y changes by 210. And she's back. Alright, so all linear functions behave similarly to the one in this example. Think of it this way. When we talk about proportions, we know that with proportions, the change has to be the same. We have that k constant that tells us that our function or our equation is going to give us a line, a straight line. So the same thing will be true for linear functions. The change has to be constant in order for it to be a line, which is what makes a function linear. So we know that based on this information, a generalization can be made that a constant change in x will correspond to a constant change in y. All right, Aria, say goodbye to everybody.
Goodbye.
All right, you're going to let me finish now? Okay, thank you. All right.
Okay, can you look at me now?
Yes, please stop.
Please stop.
All right, so the question here now is, will a nonlinear function have a constant change in x that corresponds to a constant change in y? The answer to this is yes. Again, if you go back to proportions, we know that in order for something to be proportional, the change has to be constant. And when that happened, we got a graph of a line. So it makes sense that with a linear function, the change in x and y have to be constant. For number 2, if you take a look at the function over here, so we have the function of y equals x squared. So if you take a look at the change, here we have a change of 1, and here we have a change of 3. Over here again we have a change of 1. But then now, look at my change. When I go from 4 to 9, I have a change of 5. So looking at this, I don't have a constant change between x and y, which tells me that this would not be a linear function. All right, then this next part is proving why linear functions work. And to be honest with you guys, right now, I'm not so much concerned about this. So we're not going to worry about this as of right now. We'll worry about this later on within the chapters. All right, so we're going to move to number 3. So we're going to consider the function y equals x cubed. And we're going to look again at 2 equal intervals to determine if the function is linear. So again, we have a change in x of 1, and then another change in x of 1. So these should be 2 equal intervals. In this case, when x changes by 1, y changed by 7. So in order to be a linear function, we have to have another constant change of 7. However, to go from 8 to 27, we have to add 19. This tells us that this function is not linear. So from 1 to 2 and 2 to 3, the x value goes up by 1, but the y value goes up by 7 and then by 19. Since the change is not constant, the function is not linear. Right, so then now, if you look at the form of this function, it is in the form of f of x is equal to mx plus b. And what is the name of the form of this linear function? Well, some of you may know this, but those of you that don't, it is called slope-intercept form. And this is going to be really important in later later lessons within this module. All right, graphing linear functions given in standard form. So here we go, we have a couple of vocabulary terms here. So any linear function can be represented by a linear equation. A linear equation is any equation that can be written in the standard form expressed below. All right, so standard form is the more common way that we see an equation written. So you can use that as your definition, the more common way to see a linear equation written. And then this right here, a times x plus b times y equals c, that is the standard form. All right. And a linear equation is any equation whose inputs and outputs give a graph that makes a line.
Okay, Mommy.
Okay, thanks, Aurora. So now you guys got to hear from 2 of the 3 children. All right, so here we go. Determine whether the equation is linear. If so, graph the function. So when you're determining whether or not functions are linear when they're in standard form, you have to look at the form. So here you have something times x plus something times y is equal to 10. So in this case, it would be in standard form because a would be your 5, b would be equal to 1. The reason it's equal to 1, since there's nothing there, it can't be equal to 0 because if it were equal to 0, it would be 0 times y, which is 0, so nothing would be there. So in order for y to be there, it has to be 1. Look at it this way. 5x means that there's 5 x's, and just 1 y tells us that there's 1 y. But we don't have to put the 1 in front of it. We can just say, okay, that's y. And then, of course, c would be equal to 10. Right, so instead of just going through this entire example with you, what we're going to do is I'm going to go through this example.
Mama, do I get this?
So now here, the equation is linear. Okay, so looking at this equation, you have negative 4x plus y equals 11. The equation is linear because it's in standard form. Now, it doesn't have to be in standard form to be linear, but the form that's given is standard form. And we know that because of this form, we know that it'll be a linear equation. Okay, it can also be in slope-intercept form and give a linear equation. So in this case, a is equal to -4. And again, b is equal to 1 because there is only one y. And c is equal to 11. All right, so then now, in order to graph the function, to make it easier on ourselves, instead of plugging in for x and then consistently solving for y and moving everything around, what we're going to do is we're going to first solve the equation for y. What that means is we're going to take the equation and get y all by itself. So over here you can see that when we take -4x plus y equals 11, if we add 4x to both sides, okay, if we add 4x to both sides, that'll get rid of the -4x here and put it over here. Okay, and I guess I don't have to have that x here because it's there, which I didn't notice when I wrote this, but you guys understand what I mean. So we added 4 to both sides and got that y is equal to 11 plus 4x. So then now, when you actually use this equation, okay, so I'm going to plug in -4 for x, and if I do -4 times +4, that gives me -16 plus 11 is 5. So when x is -4, y is 5. All right, and then if I plug in -2, I know that -2 times 4 is -8, plus 11 is 3.
Mama.
Now here, I
Mommy.
noticed that, and ignore
What are
this.
you doing?
In a little bit. Sooner if you leave me alone.
Mommy.
Okay, 4 times 0 is 0, plus 11 is 11.
Mommy, do I get stick?
Okay, now if you notice, we have a constant change here. For every time x goes up by 2, y goes up by 8. I'm sorry, I think I messed up some math here, so this should be -5. I knew something didn't sound right about that. All right, so -4 times 4 is 16, plus 11 would keep us in the -5s. And I apologize to those of you who caught that before me. So 4 times 2 is 8, plus 11 is 19. But notice when I did that, I was able to go back and say, okay, here is this constant change that I should have, but it didn't work between 5 and 3, which allowed me to go back and check my work. It's absolutely acceptable and appropriate to make mistakes. We have to actually go back then and check those mistakes and figure out what we did incorrectly. All right, 4 times 4 is 16, plus 11 is 27. So now I can actually plot my points and say, okay, when I have -4, so -4, 1, 2, 3, 4, y is equal to -5. So -5 is about right here. And when I have -2, it's equal to +3. And when it's 0, it's equal to 11. And 2 gives us 19. And 4 gives us 27. Now, this isn't going to be an exact science here because our graph is a little bit bigger, but notice that it does give us a line. All right, and your graph will probably look a little bit better than mine because you're not confined to what a computer can draw. So now you've seen how we can take and plug in our numbers and graph our functions. Again, we can sit here and show all the work for this, and you should be showing all the work for this, but because it's your notes, we're just kind of talking you through the first parts here. All right, so when we go back and reflect, we're going to write an equation that is linear but not in standard form. Well, when it's not in standard form, you can have an example that's something like your slope-intercept form. So you can have y is equal to 2x plus 3. Okay, that would be an example. You have to have these pieces though. You could say that y is equal to 2x because in this case you would be adding 0, but to clean up the function, because we don't have to put plus 0 because we know anything plus 0 is itself, so we just take that off. Okay, you could also have x all by itself and have x is equal to 7 y plus 4, something like that, but we typically don't see equations written like this when we talk about linear functions because it makes a lot more sense for us to solve for y because our x is always our independent variable, and our independent variable is what we have and what we can control, and then we put in the independent variable to solve for the dependent variable. So more often than not, you're going to work with and see equations that look like these. Okay, and then you know that they're linear because of the fact that they have this form. Now in this case, if a were equal to 0 in an equation written in standard form, how does the graph look? Right, so I want you to actually take a look at this and think about that a little bit. So what they're saying is, if a, excuse me, is what's connected to x plus b times y is equal to c. So I want you to actually plug some numbers in here and take a look at what your graph would look like if this were to happen, and we will be discussing that more in class. All right, and then here you have your turn where you're solving for 6x plus y equals 12. You might have done something different in your online textbook, which is completely fine. Just make sure you have your work in there. All right, now we're hopping to discrete and continuous functions. We've talked about these a little bit before. Discrete functions are functions who have unconnected points, and continuous functions have connected points. Makes sense. Continuous means that it goes on together, it connects. Discrete means that they don't connect. All right, so in this case, you have the DVD purchases, where you have a number of DVDs that are purchased and then a cost. And then here, it's a discrete graph because of the fact that you know that you cannot buy a fractional part of a DVD. You can't go in and say, I just want this full DVD and I just want half of this movie because I don't like the ending. That doesn't work. You buy the whole thing or you buy nothing. So in this case, you can't connect the graph because you can't purchase half of a DVD. So you can't have a line between 0 and 1 because that implies that you could purchase that many DVDs. And that many DVDs would be fractional or partial DVDs, and you can't do that. So let's look at the next example. So Elsa rents a booth in her grandfather's mall to open an ice cream stand. Interesting that they chose that for their example. So she pays $1 to her grandfather for each hour of operation. The amount Elsa pays each hour is given by f of x equals x, where x is the number of hours her booth is open. So in this case, if it's f of x is equal to x, and again, remember f of x is standing in place of y. So this is like y is equal to x. In this case, it would be a function, and we know this because before I talked about how if you were to say, okay, well, plus 0, that's the same thing as saying y is equal to x. Okay, so we know that when x is 0, then y is going to be 0. When x is 1, y is equal to 1 because she pays $1 for every hour. So when she has it for 2 hours, she pays $2. And when she has it for 3 hours, she pays $3. 4 hours, she has it for, or $4. 4 hours, she pays $4. Okay, this is a continuous function though. The domain is anything between 0 and infinity. Okay, because she can rent it for more than 4 hours, but she can also rent it for partial hours. She can rent it for a half an hour or an hour and a half or 2 hours and 15 minutes. Okay, she can rent it for partial amounts of time, which tells us that she can have a continuous graph, which means we can actually connect those dots that we have here. So when we have 1 and 1, 2 and 2, 3 and 3, 4 and 4, and then again, we know that this goes on forever because she can rent the stand for as long as she wants. Because of this, then, we know that the range would also be anything from 0 to infinity. Now, we know that it couldn't be anything below 0 because you can't rent a booth for a negative number of hours, okay? Time, in this case, time can't go negative. All right? So why are the points on the graph connected? Well, we talked about that. They're connected because of the fact that she can purchase the booth for an hour and a half. She can purchase it for a partial or fractional amount of time. Okay, how is the graph of the function in example 2a related to an arithmetic sequence? Well, in this case, if you look at 2a and the arithmetic sequence, remember arithmetic sequences have to have the common difference. So in this case, every single time that our position goes up, so when we go from 0 DVDs to 1, the cost goes up by 2. We go up by 1 DVD and the cost goes up by, so up by 1 DVD, the cost goes up by 2. Up by 1, up by 2. So because of the fact that this function has the difference is always the same, that's where it is like an arithmetic sequence. All right. So then now you have Christoph, who rents a kiosk in the mall to open an umbrella stand. He pays $6 to the mall owner for each umbrella he sells. The amount Christoph pays is given by f of x equals 6x, where x is the number of umbrellas sold. And graph the function and give its domain and range. Okay, so now again, think of what kind of domain and range you can have and what kind of graph this will be based on the information that you're given. Right? If you're having trouble with the online book, just complete the your turns in here and we will absolutely talk about them. And as always, if you have any questions, please write them down or email me so we can go over them in class.